Hi, and welcome to the FabLearn conference. So we are on day 3. We're in our full paper panel of the 3rd session. Today we brought together 4 papers that are going to explore this overarching theme of tools, materials, and artifacts. And so we'll be together for the next hour until about 3:20 Eastern, if you want to join us. And we've got the following 4 papers. We've got tools for biomakers, reviewing affordances and challenges for K-12 hands-on making with biology. This is presented by Yasmin, Kafai, and Justice Walker. We've got a second paper on making despite material constraints with augmented reality mediating prototyping with Sowmya and her colleagues as well. So this will get us both into thinking about biomaking and also into AR prototyping, 2 new areas of the maker realm. And then our third presentation will be by Vanessa Svihla on what GAZE data reveal about material agency, resilient makers, materials, and ideas. And our final presentation will be by Fayette and colleagues on characterizing student artifacts in a multidisciplinary biomimicry and robotics unit. And so we've got lots of new ideas about material agency, kind of taking us into the post-humanist realm. We've got biomimicry and kind of thinking about that in 2 of our presentations. So this is an exciting area that we will be exploring together today. I'm your chair, Kylie Peppler. I'm an associate professor here at UC Irvine, both in the informatics and in the education department. And I'm excited to be part of the presentations with all of you. We will ask each presenter to share their slides, and then we'll ask about 2 to 3 questions following the presentation. We've asked everybody to stick to about 8 to 10 minutes, and then we'll close our session with sort of a larger Q&A forum, that our folks that are watching the conference live and or our co-panelists can ask of one another. All right. With that, Yasmin, I'm going to go ahead and just turn the screen over to you.
Okay. You should all be, thank you very much. I'm here to talk about tools for biomakers, which connects really nicely to last year's FabLearn keynote by Sylvia Martinez, pointing out what the next revolution will be. And Justice, together with Justice Walker, who is now at the University of Texas, El Paso, we looked at the affordances and challenges of actually K-12 hands-on making with biology. So what is actually available for kids? And I mean, as you know, this conference is strong. I mean, we have a history of many tools and construction kits in K-12 education, from the Froebelian gifts, physical, digital tools, textile hybrids, and just a moment ago at the hip hop panel of music making tour, there's an abundance of tools and construction kits. But what does that actually mean when we move into the area of bio design, DIY bio or biomaking, which, by the way, I mean, a movement which pretty much parallels the start of the maker movement. And when people talk about designing synthetic biology application, they really kind of see a lot of commonality with computational design, because you assemble genes in a specific way and create toggles and circuits and are able to produce desired outcomes. In a short way, we turn cells into manufacturing units to kind of create new applications. And there's already a whole world of applications of biomaking out there. I just listed a few here, like sustainable cement, which is grown in microorganisms, Arctic apples, which you can find in your local supermarket. They have a gene switched off so they don't brown anymore. In clothing, North Face a few years ago presented a jacket made of spider-like silk, and Adidas sneakers. And then, very importantly, even in the medical field, insulin from microorganism, especially for those people who are allergic to the animal-produced insulin. So believe it or not, applications of biomaking have already made it out of the lab into the real world. And one thing Justice and I thought about it is, can we think about the things we want to make with biology? And I want to make reference here because this year's honorary speaker was Cynthia Solomon, who more than 50 years ago wrote a really influential paper together with Seymour Papert, 20 Things to Do with a Computer. And believe it or not, if you read this paper, I think you can find the link in the chat. Many of the things they propose, people probably thought at the time were totally, I mean, in the future awake. And likewise, when Justice and I, for the Constructionism Conference, thought to write 20 Things to Make with Biology, the paper is, by the way, available, even though unfortunately the conference didn't take place. We came up with a whole list, easily a list of 19 things, and then of course the famous 20 recursion line. And many which you see listed here, they are actually, that can be already made by yourself in community labs or other places. Some might be a little bit further along. So we think the time has come to think about making with biology. And there are, of course, tools out there which are quite expensive, even though the price has come down. People even make their own, I mean, in DIY fashion, if you believe it or not. And I mean, this year's Nobel Prize for chemistry, after all, went to the two creators, Doda and Charpentier, for developing CRISPR, which allowed very precise manipulation of genes. So we looked around, what are the kind of tools out there? And there's a few who have started, among them the work of Orit Scher and Amanda Strohacker, or even introduced Crispy for very young kids, early elementary, to design their own fireflies. Synflow kind of brings in blocks which you can move around and put together. And the San Jose Tech is actually the first biomaker space. They have a simulation also co-designed by Orit Scher, where you simulate life on Mars and kind of need to kind of create new things. So there's a whole range of kind of simulation tools which make the kind of biomaking accessible. And then in the past few years, a number of wet lab kits have kind of become available. MIT People Focal produced BioBits, which is frozen material. And if you put it together in the right way, you have fluorescent materials, bento box, DNA and Playground, and also Biomaker Lab, which is something which Justice Karen Hogan, Orkan Talan, and I have developed, actually get you to work with real DNA material and go through the whole process of incubation, transformation, and creating new materials which you can use for designing new applications like enriched cakes or biosensors or colors. And what we did in the paper, you can read this for more detail. We decided to kind of unpack a little bit what we mean by tinkerability, which is kind of like a very popular term in maker education. So perceptibility is really important, making things visible, immediate feedback. And I just changed the name. I think it should be explorability, enables learner to explore materials and iterate designs. Expressivity refers to the personal customization. I think we really value tools which facilitate that. And then usability. So when we looked at all those tools in that labs, and we found, lo and behold, they're really good on perceptibility, and a little bit less so on explorability. But two of the aspects, expressivity and usability, are really not part of many of them. So I think we still have a long way to go in terms of what are the accessible and affordable tools for K-12. So, you know, one of the challenges, of course, is that they work with microscopic biological processes. So the tools really place an emphasis on making them perceptible, and to some extent give some hands-on explorations, and products can be made which are personally meaningful and usable. But I think, you know, there's some critical issues which we need to consider in future tool design and activities. So these limited opportunities for explorability, how can we improve this? And then also the considerable black boxing of the cellular activity. we really have to kind of think very carefully, what is the right level here? I mean, what do we need to make accessible? Like in computer science, kids don't program or make with 0 and 1s. We have created all these interfaces. So I think one thing which has been really important to us as over the last 5 years we have engaged in biomaking, it helped us to kind of revalue critical aspects of maker activities. There's a value in learning pipetting assembly practices as much as the tinkering practices. I think you heard this also in today's keynotes. There really should be a new appreciation for different materials. We're so used to work with digital and physical materials. The living media present another world. And then finally, I heard Mike Horn say this yesterday in the Mike Eisenborn panel, crafts and tool use needs to be valued as well. I mean, we're trying to get kids to kind of create products, to make them so quickly. Let's kind of slow down and also value kind of the materials and crafts which people can learn. If you want to, I mean, one particular example also presented at last year was, of course, the Grow It Yourself construction kit by the Nest makers, which I think is a great example of how young people already are entering this domain. So I want to conclude with a quick pointer that we just released a workshop report on how to bring Learn, Design, Bio into K-12 education. You should have the link in your chat so you can download it for free. Thank you very much.
Thank you, Yasmin and Justice. What amazing. This is great. So we're going to open it up to some questions. I'd encourage our panelists, to pop in with questions. Yasmin, as you were noting, the example of, kind of just working with pipettes and, measuring tubes and, just all the language that happens and the materials and how to operate them, or even just using a scale and so forth. It reminds me of sort of my introductory chemistry class where, the kids coming from all of the rural schools had never had a chemistry lab. And so they were just lost in the language and they just had no idea what a beaker was. And they just had they were surrounded with all this glassware and they couldn't find the right thing. And so, being able to name and talk about and use these kinds of maker tools is just really excellent. So I've got a question, and folks, just turn on your video feed from the panel if you have questions as well, and I'll just call on folks. But I was wondering, for maker spaces and or maker educators that want to get started tomorrow, what's the best introductory kind of kit? Like what's the make and or the tools to have on hand to get going?
Really great question. And Justice and I were in parallel at another conference, the Global Bio Summit. So something which Zoom makes possible to be in two places at the same time. And there you have a worldwide community of people who have labs, tools, who are really concerned on making DIY bio accessible. And the previous example, which I showed you, by the DIY BioBorders, they used kombucha and mycelium. I mean, kombucha you can find in any pantry. It takes, 2 or 3 weeks before you kind of get some leather-like materials. And mycelium, I know that the San Jose Tech Museum, the bio workshop, has used it extensively and without problems. So those materials are already all, I think, good starter activity, in particular for younger kids. The other kits which I presented, like BioBits, you can buy them off the shelf. Mycelium, also there is a company, Evocative, where you can get all these materials and suggestions. So I think, there are, the toolkits are there, and some of them can be done at home in your garage and existing maker spaces. And the other things you need kind of, some more introduction on how to handle those.
Great. Maybe one more question. So if you had to leave us with just one bioliteracy from your from the pamphlet that you developed on the critical bioliteracies, what's the one that you think most maker spaces should start to advocate?
I really think it's a great introduction into the consideration of ethical issues. There's so much fear associated with design bio. So by making it, I mean, you begin to better understand what actually is involved, and you can use this also for a wonderful context to talk about sustainability, food security, all of those issues which are really critical today.
Yeah, wonderful, wonderful. Thank you, Yasmin. Thank you, Justice. All right, Sowmya, go ahead and share your screen.
Sorry, just setting up. Can you see my screen?
Looks great, yes.
Okay, great, thank you. Okay, so hello, my name is Sowmya Somanath, and I am an assistant professor at the University of Victoria in Canada. And today I will be talking about our paper, which is titled Making Despite Material Constraints with Augmented Reality-Mediated Prototyping. So in the short talk, I will briefly cover some of the motivations for this work, show you a prototype tool that we built, and share with you some lessons that we learned. So to begin, imagine the scenario where you're trying to build a physical computing project using electronics, and you realize that you don't have access to some of the materials that you may need. So you don't have immediate or easy access to them. In such a scenario, instead of stopping our exploration and playing with these ideas, can we continue playing with our ideas and instead tinkering and make do with what we have instead, and use technology to support that sort of resourcefulness? So that's sort of the question that motivated our work. And in response to this question, we looked at exploring augmented reality as a way to enable people to build circuits with the materials that they have at hand. And what they don't have, they substitute by using a stand-in AR component, as you can sort of see in this image, where I don't have a speaker, but I can sort of use a AR speaker instead to build the circuit. So I'll show you an example of this first and then get into the details. So let's say you want to build a simple lamp and you need a button and an LED for it, but you don't have a button. So the way to do this with augmented reality mediated prototyping would be that we build the circuit like we would with all the components. And for what we don't have, we use a stand-in placeholder, which we can then augment with whatever is missing. We can program the circuit as if it were one unit, and then we can interact with both the physical and the digital. So the idea of augmented reality mediated prototyping builds on existing works in literature, such as the Light Up and Conduct AR, which looked at how to teach people about electronics using AR. So our work sort of builds on these ideas and isn't so much focused on teaching people circuits and electronics, but much more on how to support them in low fidelity prototyping and continue to explore their ideas. So the AR-mediated prototyping, the base vision consists of many design considerations that we need to think about. So one is the physical and virtual form of these AR components. That is, should they be physical replicas of these components that we don't have, say built using a clay or something else? Or should they be simply stickers that we can attach on any physical object that can act as a placeholder? Similarly, for the virtual form, should this be more realistic renderings of these objects that we are missing, or should it be more abstract versions of what we are missing? So definitely some considerations there. The other aspect to think about is circuitry and programming. That is, do we want to make this a simple circuit building exercise, which may be enough for a low fidelity prototyping tool, or do we want to sort of enable better transferability of skills and mimic real circuit connections? Similarly for programming, do we want to use existing platforms or do we want to create others? And third, this design space also needs to look into how do we interact with these AR components? That is, do we want to interact with them using on-screen widgets on our phone? Or do we want to interact using gestures that are similar to how we would interact with a physical component, say press a button or close a sensor? Or do we interact with the sensors that we have in phone as a substitute for what we don't have? Or should we directly interact with these physical placeholders that act as proxies for what we don't have? So the space for AR-mediated prototyping is relatively large, as you can kind of see from this image. So we took a few of these options to put together a simple probe that we could then explore further for learning a little bit more about AR-mediated prototyping. So the probe we put together is called Polymorphic Cube, and it consists of two parts. The first part is this physical object that acts as a placeholder, in this case, a cube, and to which we can stick a QR code that will allow us to augment stuff. And from an electronic standpoint, it has the footprint of an LED, essentially. And the second part is this companion smartphone app, which allows us to augment these components with the missing electronics that we may need for our prototyping. So in this case, you see a servo being mapped to the polymorphic cube. So both of these parts can then allow us to continue prototyping and exploring our ideas. So in order to understand the strengths and limitations of augmented reality-mediated prototyping, we conducted a two-part study, which is preliminary studies. So the first one we did was to have people come into our lab and try out using the polymorphic cube. And the task was that they would all build 4 unique versions of a controllable lamp using the polymorphic cube in different configurations. So as an input, output, sensor, etc. And then based on the results of that, we conducted a follow-up questionnaire study where we asked people how they would like to interact with these AR components, especially if there was a variety of different types of components. So there are several lessons that we learned, but today I'll briefly give you an overview of some of the things that we got and kind of mostly use it as a way to talk about where to take this further. So overall, what we learned was that most of our participants had in the past faced a situation where they didn't have access to something that they needed right away. And because of that, they had faced situations wherein they were delayed in exploring their ideas, or sometimes they just forgot the idea that they were trying to play with while they were waiting for the components to become available. Or in other case, they kind of just gave up on that idea and went to do other things. So in such situations, our participants found AR-mediated prototyping as a way to help them keep going. One of our participants said, if I open my box at home, I have all of these, such as button and LED, but I don't have a servo. So it was cool that we started with the servo because I actually tried what I could have done at home. Because I did not have a servo, I simulated it, and it was really helpful. We heard similar such comments from our participants. So overall, there was some promise in this direction of AR-mediated prototyping for our participants' feedback. Now I want to talk about 2 things that I think have really, I believe, have interesting directions for taking this further. One is scalability. So in the study, all our participants used only a single polymorphic cube to build the circuit, but we all spoke about this idea of using multiple polymorphic cubes in all sorts of contexts, such as in a classroom or in a lab when you're just trying out things. So there are definitely some considerations that need to be made with scalability. So from an implementation standpoint, this is definitely possible. We can track multiple cubes, we can augment as much information as we want, and it would be fine. But from an interaction standpoint, I think there are some interesting questions to consider. So for example, what if these cubes were spatially quite apart? So for example, let's say I had a cube on my clothing and I had one at the back, and it doesn't have to be a cube, it could just simply be a sticker that's at the back of my shirt. So how do you then interact with these? Perhaps we want to explore ways that expand our peripheral vision. We may also want to go away from this sort of using a phone and sort of explore more hands-off, other options such as a head-mounted display where we have free hands to explore. The other area for scalability is what if multiple people wanted to use such a prototyping tool and do collaborative tinkering or prototyping of ideas? So one thing that we've been thinking about is what if these stickers or what if these components could sort of be shared with people, almost like pieces of puzzle that you put in a portion of your idea, pass it on to the next person who can continue to build on it, or maybe there are other ways to do this. So that's definitely, I think, a direction to explore further. The other direction that I think is interesting to explore is the physical kinematics aspect. So as we all know, with physical computing, one of the main draws for most people is because we can see things happen physically, we can feel things move, and it affects other things. But of course, with the AR component, this isn't possible. That is, we see things move, but in order for it to actually affect a physical material, we would currently, at least in a low fidelity prototyping environment, have to do it ourselves. So similar to a visit of force technique, where I see the servo move, and then I would take the cube myself and start moving it perhaps. But I think there's some really interesting ways to sort of enrich this experience further. And I think it builds on some of the ideas that we heard from our keynote speaker, and also some of the ideas that Yasmin just spoke about. That is looking at materials that are more responsive, building these polymorphic cube-like objects from things that are, say, shape-changing displays, or they are more 4D printed objects. And then the AR becomes not just a medium to look at this component, but a way to define dynamic behavior, allowing us to create not just the electronics that we have at hand, but also perhaps new components altogether. So I want to leave it at that, and I want to wrap up. And I think definitely this project raises more questions than it answers, but I would love to take any questions. Thank you.
Wonderful. Thank you, Sowmya. You know, it reminds me of, you know, the physical limitations of like Legos back in the day, and then kind of moving to Minecraft, right? You know, it was always our fantasy just to have every piece available to us in infinite quantities, and what could we build, you know? So I think this is really exciting. What's the one, you know, question that you have that's going to guide the next phase of your work? What can we expect from you in the next year or so? Where's your next line of inquiry?
Yeah, that's a really great question. I actually just started my faculty position here at Victoria, so I'm just starting my lab. So one direction that I'm really interested in is actually very much in line with what Yasmin and our keynote speaker were talking about, is looking at materials themselves and looking at how they can be made more dynamic and afford more interactions. So one of the directions that I'm interested in is looking at sort of more responsive shape-changing displays. So we have like a single piece of object that can transform into different pieces of electronics that we can then plug in however we wanted and start using these sort of more hybrid prototyping tools in a more convenient way. So sort of trying to, and also do it in a somewhat low cost way so that we can have more people try it out and try it out in different contexts, such as a classroom or in an art environment or a craft environment. So that's definitely, I think, a direction that I'm interested in exploring, that is making materials themselves more responsive.
Right. Yeah. And, you know, it reminds me, you know, there's a cognitive psychologist that I'm working with, and he's been kind of thinking about kind of AR, VR, XR environments, and how, you know, you know, when you were saying like the physical environment and sort of what is kind of brings us joy from working in them and kind of seeing things and feeling the motor, right? You know, there's just something to it, and that tangibility. Have you thought about kind of you know, translating any of that to you know, to your prototyping environment and to the AR mediated portion, so you get that physicality, or what are your thoughts on that?
Yeah, that's a really good question. So I think there are some things we were thinking about, especially in the context of this project. One is to sort of provide some additional like feedback. And of course, this project was motivated by the fact that we don't have access to everything. So we didn't want to just simply keep adding more stuff to the phone, but the phone itself can provide more feedback, like it can provide vibration. It includes sensors that we can leverage to sort of accommodate for things that are missing. We can, instead of also programming on a separate environment like an Arduino IDE, we can start programming on the phone. We can start creating and adding more stuff through the phone. So I think that's definitely one direction to go with, like trying to provide haptic feedback or trying to provide some of that physicality through the phone. And then the other is, like I was kind of talking about, like to have materials in the circuit building that are more responsive, and then use the phone, the AR medium, not so much to just visually visualize and see things, but to provide more input or author more dynamic behaviors for these kinds of mediums. So perhaps I sketch how a responsive shape-changing display should work, or I create other patterns saying, now you rotate, now you're a translating object. So that's kind of what I'm thinking. I don't know if that answers your question.
Yeah, thank you, Sowmya, for that. All right, well, we'll come back to a full set of questions towards the end of our session. Vanessa, go ahead and drive your slides.
Let me just hit, oops, present. All right, so I am Vanessa Svihla, and I will be sharing our study on gaze data that we've been using to look at material agency. So you're in a makerspace. Here are some materials, make something. How will you decide? We have, looks like some coin cell batteries, maybe some e-textiles, some Legos, puff balls, all kinds of different things. So as we think about people making things, their agency, their sense of making decisions matters. But are all decisions the same? I think a lot of the time when we talk about agency, as we've talked about it, even against identity and learning, it's not very well theorized in our field. And so a lot of times agency is treated just as making decisions and as if all decisions are more or less equivalent. But we know from our own experience that's not the case. And so I define framing agency as making decisions that are consequential to how the problem is framed and therefore how you might go about solving a problem. Also of relevance here is, does it matter who makes the decisions? So we know in typical kind of K-12 settings, in classrooms, the teacher holds quite a bit of the power and makes many of the decisions. If you are making decisions about what materials to include in a makerspace, you are making the decisions. As a maker, as someone who makes things, I've made decisions about what's here in my sewing room that is now my home office. In this case, we're thinking about agency as shared with others, and also from a post-humanist stance that materials also have some agency. Sometimes they speak to us, they tell us something that they want to be or become. And so to kind of think about this idea of material agency, we're talking about using just an example of Legos as a way to kind of set up a framework. And I think this is a really nice connection to the past two talks. So we think about being materials that are sort of just present. They often exert some kind of covert influence. So Legos are rather coercive in this way. They tell us very strongly how they're supposed to go. But sometimes we can treat them as doing materials. So in our conversations with them, we might ask them to do something. Like in the middle, we see the studs are changed 90 degrees. And so this is a time where we do something. We look for a material to do something in a design. And finally, we take this idea of becoming materials. So this is an agentive repurposing of materials where we actually treat the materials as something that gets designed or some design work in conversation. And so here that typically unfolds interactionally as we see what they might offer, what else they might whisper to us, or for instance, in this case, gluing googly eyes onto Legos or slicing studs off, which is a shocking thing to do in front of students. So in this work, one of the questions we're investigating is how might the resilience of makers, materials, and ideas shape agency negotiations and reveal framing agency? I teach a creativity and technical design course, and we really emphasize the idea of documentation of process, really trying to get students to document and reflect on their creativity across materials over time, specific strategies they can use. So we make available to students a range of ways to document their practice beyond the phones they already have in their pocket, from head mount GoPros to a ceiling camera and to eye tracking. And so in this study, we're looking at some of the video from the world camera, so what the student is looking at with the gaze data. And you can see, for instance, the little yellow circle tells us when there's a fixation. In this video as Fabiola is looking around at materials. We transcribed these interactions with materials and conducted interaction analysis. So in this case, the task was to light up some Legos. And the focus was to get them to persist with materials that resist being used together. We provided scissors, copper tape, wire, Scotch tape, Legos, LEDs, and coin cell batteries. These materials misfit. So even when you have someone who's experienced both with Legos and with circuits, this often ends up being a task that takes around half an hour to 45 minutes. The Legos just don't fit in well with the coin cell batteries. The tolerances are tight on Legos, and so the copper tape is difficult. But I want to emphasize here, we didn't care at all whether they learned about circuits. That was not our purpose in this class. It was really getting them to persist with materials that resisted being put together. And the two women that I'm going to talk about are Jessica and Fabiola. Jessica was familiar with Legos. She had some circuit knowledge, which gave her a sense of apprehension about electricity. She didn't have a lot of experience, and so she was a little nervous about the coin cell batteries injuring her. Fabiola, who grew up in another country, had never worked with Legos before my class, and she had never built a circuit. I'm going to be very brief here and encourage you to read the proceeding. But Jessica displayed framing agency very early. She had a very resilient idea as she worked. She interviewed materials. We see from the gaze data that she doesn't just stare off into the massive pile of Legos in front of her, but that she searches for certain things. She picks things up and considers their potential, looking for their ability to do specific things in her design idea. But the materials were very resilient and they disagreed with her idea. As she worked with these disagreeable materials, she treated the copper tape as a becoming material, asking it to close the gap between misfit materials. Now, this sometimes created other problems in her design idea because sometimes these misfits led to situations where she couldn't close the switch to turn things on. Fabiola mistrusted the materials. We provided an example circuit on the workboard in front of them, and this example circuit turned out to be a very resilient idea for her. The circuit, in this case, retained framing agency. The Legos disagreed and did not cooperate as she worked to try to recreate the circuit on a flat door, and then as she worked to build a lampshade for her light. But in this process, it revealed her willingness to persist in a task that was rather obscure to her. So as we look at these two women working through these kind of funny materials that were just fairly new to them, we see that both women were resilient makers. They did little reframing. This was a very early activity in the semester. So we really wonder if they felt this sense of, in order to get a good grade, I have to get the light to go on or have to have it work, which absolutely wasn't the case. We were still starting to help them understand the importance of process and this idea that the documentation and reflection on process was what we really valued. But it takes several weeks before students really start feeling that and trusting that that's the case. And so as we put more emphasis on the value of process and on providing tools for learning how to frame and reframe problems, we wonder what kind of activities would they have done? Would they have reframed the whole task? We don't know. Finally, I just want to say that the gaze data we found to be much nicer than head mount video. The head mount video, of course, is nice. You get first person point of view. If you're like me, you also get quite a bit of nausea trying to watch and rewatch and analyze that kind of video. Additionally, the gaze data gives us a lot of information about the extremely rich search patterns that students had as they were trying to go through this massive pile of Legos in front of them. And so I encourage you to look at gaze, the eye tracking sets, not only for their quantitative data that they provide, but also because of the great video that you actually get from them. And I'm happy to answer any questions. And I will go ahead and stop sharing.
Thank you, Vanessa. Yeah, you know, it's really kind of fun seeing you focus in on sort of bringing the post-humanist and sort of the agency of the materials. I think we've all experienced that with Lego, like, just pop on here, you know, can you just do this thing for me? As we kind of go through. And I love the way that you framed this idea of, you know, persist with these resistant materials, you know. It's really interesting, you know, is at the tinkering studio at the Exploratorium, they kind of have a similar sort of principles that they don't want them to fit together too well. You know, so they've got like kind of a large wall where they're kind of creating kind of a Rube Goldberg kind of machine, but they want things to sort of pop off, right? So people don't watch them, but that they're engaged with them over time. So we see the same kind of principle coming up at other maker spaces. You know, as you were choosing your materials, you know, what made you focus in on the sets of materials that you had, and you know, how did these become kind of an iconic set? You know, what might other makers or maker spaces start to look for?
So in this class, we do use quite a bit of different things. So this is maybe the second week of the second lab they do. There's also an upcycling one. We have a number of different kind of low fidelity materials. I teach the class in a fairly lo-fi maker space / seminar room. And so although we have a 3D printer, there's no ventilation, it's a historic building, so we couldn't add a whole lot of super exciting stuff. And so we decided to be that stepping stone on campus instead of trying to be fancy. And I actually think it's a real affordance of the space that we get to look at more lo-fi tasks and let people not get so attached to their ideas and be more likely to iterate. It's a space to explore that kind of framing and tentativeness that I think is harder to cultivate when things look final and fancy.
Yeah, I think that's you know, it's a really kind of interesting idea about you know, picking the right materials for learning so that they're not you know, sort of market perfect materials that all fit together.
Although I will quickly say people really are uncomfortable when you mess up Legos. It's like sacrilege. We did a whole series of breaking Legos, and it is very uncomfortable for people who've grown up with them. So wow. I think there's something productive there too, actually.
Fascinating. Yeah, it's almost a Freudian kind of thing. Yes. We've got a question from the audience. You know, so Lillian is saying, how did the eye tracking data and directions and stairs help you to understand the discussion between the subjects and the materials? And maybe you want to say a little bit about just how eye tracking data works as well.
So in this case, we have the video of what their field of view, and then there's a little dot that tells us what they're looking at, and we get some information about how well calibrated that is. So we get information about whether or not they spend enough time to qualify as a fixation, meaning they're probably looking at something, and if they then jump, their eyes jump from one place to another. All of those things tell us something about, I guess, are they searching for something? Is there something specific? We see sometimes their gaze darts around. It is a mess. I mean, it is an absolute chaotic mess that they're working in. And it would not be easy to, you know, put QR codes and make the space kind of resolvable because it is deliberately a mess. We want it to be. And so I find it really helpful to, we defined some specific types of interactions. So like candidate selection, interviewing, rejecting, these kinds of things. So in the proceeding, we give a longer description of how we coded those different types of interactions.
Great. Well, thank you, Vanessa. You can see you've inspired a lot of people to think about. Ryan Kane adds that he loves that makers have the permission to break the rules of Lego and hacking off the studs and need to try it. I saw Faye, go ahead and start projecting your slides. I saw, you know, there's a couple makers I know that just want to blow up an LED, that you're not a true maker until you blow up your first LED, you know, and so that's your first project is to explode it with eyewear. All right, so Faye, go ahead and start your presentation whenever you're ready.
Okay, and now I'm muted. Okay, I'm at the end. All right. Can you see my title slide?
We can. It looks great.
Right. Excellent. Okay. Hi, I'm Faye Shaw, and I'm at Tufts University. This is work with Turk and Educational Research Consortium, and this is the BioRobots project. We've developed an interdisciplinary curriculum combining biology, robotics, and engineering, and we wanted to make it life science standards aligned, because when we have teachers try to integrate engineering or computer science, robotics, a lot of things we hear are, we don't have time, I need to cut something out. So the biology is standards aligned for that reason. And then we looked at a design challenge, and we looked at biomimicry used for this design challenge. The design challenge we chose was an earthquake disaster scenario. It's not safe for humans or well suited for wheeled robots. So we're going to look at animals and their adaptations and how they dig. Yasmin Kafai went through a great overview of biomimicry. On the left, we have an example again of that hook and close Velcro. And then on the right, we have a kingfisher. It dives into water to catch fish without a splash. And this shape of the beak was used to optimize the Shinkansen bullet train. And we use biomimicry in a context to take the solutions from nature and then apply them. So an overview of our curriculum, it's about 4 weeks long. The first is animal analysis, where we have the students identify the important digging structures. We have them also learn how to program the hummingbird bit using MakeCode. They sketch their design and build prototypes and iterate. And finally, they share out. They are documenting through the whole thing, but here's an example of a student poster. So this work reflects an academic year of collecting data. In 4 schools, we have teachers in both science and technology, and we collected video and audio, field notes, interviews, and we really wanted to see, how does the curriculum show up in these student artifacts? So in our curriculum, we're looking at what are the mechanical characteristics in these solutions, and to what extent do they mimic the animal. And we're going to look at their structure, the animal structure, and then the animal motion. We chose these 4 animals for their digging properties. A pocket gopher does scratch digging, much like a cat or a dog, and you see the big paws and claws. The mole does a swimming kind of digging. That path, the figure under the mole is a pathway for how the paws move. And then its structure includes the paws and the claws. This pangolin has quite large claws to hook into an anthill and then pull back in a strong motion. So that AB is like pushing out, and that BC is digging into that anthill. The mole rat uses its very large teeth to chomp open and close, and you see in the picture of the animal. And note the mole and the mole rat, you're going to talk about them, but it can get confusing. It can be between mole and mole rat. So we looked at each robot's mechanism, their structural biomimicry, what the animal looks like with respect to their digging adaptation, and then how that animal moved. The mechanisms, we taught the students how to do this and had building guides. The ones we saw were the direct drive, where something is just attached to the motor, a linkage, where there's a link like this popsicle stick, moving a secondary link, and then the cable drive, where you pull a string and the end of it is actuated. The direct drive is the simplest, and we saw that the most often. So again, here's that mole rat, and it's going to chomp on that dirt with this open close motion. And this is the robot built with this inspiration. So if you see, the mole rat is coming up to the dirt and really using the mouth to move the dirt. And then on the right, we have the robot move its jaw up and down. So you can see the direct drive, it's attached straight to the motor. The red part is like the top teeth, the yellow, the bottom. There are these little black straws on top, which actually don't do anything. But you can see these teeth mimicked, and then you can see this motion, this back and forth. And we considered this a strong motion by mimicry. So we looked at what appeared by animal, and we saw that when we scaffold with directions to build direct drive, linkage, and cable, the students are able to do this. They do use the direct drive most often. It is the simplest. And this is how it looked by animal. We also saw, this is the part, what the most excited part about this. We're most excited that we see that most of the animals do express some biomimicry, that these paws and claws, and then the mole rat is the only one that has teeth. But we really think that the students got it because we see these features of the animals, these structures show up in their robots. Lastly, we don't see a lot about motion biomimicry, but we hadn't emphasized this in the curriculum. In the curriculum, we mostly talked about structure, the structure of the animal that it uses to dig, that supports the digging function. And when we tried to figure out what it meant to be biomimetic, we decided to boil it down to the structure and then this motion. But we do see there are some cases where there is strong and some biomimetic motion. So in future work, we're hoping to characterize how teachers emphasize this and what results from these robot artifacts. And then we want to incorporate some of the other sources, including the worksheets and interviews of both the teachers and the students. We would like to thank NSF for their generous funding and our superheroes, our teachers, for teaching this curriculum.
Fabulous. Thank you, Faye. It's so fun to kind of just see how, what kind of inspiration that you're taking. In my assessment, I think so many of our toolkits, kind of overlook sort of this electromechanical kind of creativity. And so it's really fun to kind of seeing you sort of unpack some of the inspiration from nature and trying to get the kids to imitate these kinds of things. So it's really fascinating. So thank you for bringing that to us.
It was definitely like changes from our first year. We left it pretty wide open and said, any disaster scenario, any animal. And so they didn't quite have the depth that we wanted. It was fire, elephant, water, trunk, and it's like one word. So we said, oh my goodness, how can we enable really deep understanding, really deep engagement? What are the affordances of each animal? And we provide handouts and videos, and I think gestures are actually my favorite. When students gesture, and they pretty much all, like, without this kind of diagram for the mole, that may be the most complicated, they all agree how they do it. It's like, oh, people swim, moles swim. So having this rich set of animal resources really enabled the students to go ahead and do the animal analysis, look at the parts, look at bone structures and things like that. And by constraining to an earthquake scenario, by constraining to 4 model animals, they had a much deeper engagement. And then I think you see more of that. You see more of that in their robot artifacts.
Right. Yeah, I think that gives you a sense of like a creativity principle that's kind of coming there, is that not by having access to all of them, right, but by just looking at a few and kind of going in deeply, because it's just the range. You might normally just kind of group all of these animals together, but now looking at the subtleties of this, can inspire a lot of creativity. You're getting a lot of love from Yasmin and Sowmya and Cherishi as well. Just looking at that movement mapping to the animal behavior, and you hear this again and again. We work closely with biologists and other folks in the field and chemists, and how much of their innovation actually comes from this closer observation of real life. So I think that's fascinating. Yasmin, I don't know if you have any questions for Faye, given that you're doing similar in this world of biomimicry and biomaking.
Well, we're not doing quite the same thing usually, because we're really designing a new materials which are not exist really in nature. But I love this idea of kind of, it trains observational skills. I mean, this is in some ways classic science inquiry and observation, and then using it as an inspiration to get students think about kind of what can be made, how that can be emulated, and how sophisticated some of these animals are within their very constrained settings of what they need to do in order to survive. So Justice, I don't know whether he is, because last year at the Biodesign Challenge, one of the teams actually also started out with biomimicry to kind of understand on how to design new applications.
Yeah, if I could also assert a thought here, what I think is really fascinating about this activity is that, and even thinking about how you pointed out that you had to constrain it a bit to sort of move them along, it seems like an interesting stepping stone sort of activity to the way we're thinking about biodesign, right? There's also biomimicry and biological processes, right? Like, how do you leverage the way microbes decompose carbon or recycle it to be applied to other design challenges, much in the way you do? That's a super complicated idea, but to begin to think about what the sort of material and outcome consideration learners are making as they begin to design is so fascinating here. And I wonder what this might look like down the road. Thanks.
I love there's so many overlaps. I feel like at some point we had talked in our group about textures, how that makes me think of Yasmin, you said with the biodegradable like shoe platforms. And we were thinking, like, if you look at the scales of the pangolin or like scales of snakes, that's what can get them to move. So there definitely is that more detail we can dive into. I love what Justice said with what can be the next step. And I think and the processes makes me think of like self-assembly and self-organization of birds and things like that. So I feel like there's so much that we can borrow.
Yeah, thank you, Faye. And Vanessa and Sowmya, I don't know, if you've got any questions, but Vanessa, it did make me kind of think about, coming back to your notions of agency and sort of distributed agency. A lot of times we place the humans as center, but you can kind of see how, the animals and the materials in your case, in your studies, start to decenter our focus solely on human agency.
Yeah, I think it's been a very productive lens to take. I encourage others to. I think it's productive in part because I once at a maker fair back when the world was a thing that had like face-to-face gatherings in it, talked to a parent about the idea of materials talking to you and called it materiality. And an hour later, I heard somebody else who hadn't been there use the term and teach someone else. So it tells me this is a theoretical idea that has teeth, right? That has some value in the world.
Yeah, absolutely. All right. Well, thank you all for joining us today. And there's a few more events left on the concluding remarks that are up next. So go ahead and just join that Zoom. I think the link has just posted within chat to make it easy. And then also the Young Maker posters. So please join us for those two ending events for this weekend. Thank you for joining us and enjoy your making.